Good morning, good afternoon, and good evening to all the listeners. And if there's anyone from the east side of the globe, good midnight. Today, my talk will be based on a work in collaboration with Jung-Wook Kim. Sorry, that was an alarm. Which is a sum rule for tidal love numbers. And the main result, which this talk is going to basically revolve around, is this simple, nice little equation. And my talk will consist of two parts. So in the first part of my talk, I'm going to explain the physics behind this rather mysterious looking equation, which I'm sure you'll understand in 5 minutes. And in the second part of my talk, I'll speculate on what we can do with this equation and why you should care if you care about black holes, quantum black holes. So as usual, we'll be using natural units. And on the left-hand side, what you see is the love number, which gives you the tidal response of a body. So here, we're treating the system as a point particle with spin zero, which is kind of standard thing when you use amplitude techniques to study gravitational two-body dynamics, classical two-body dynamics. And the normalization is something that looks like this. So this is the world line operator, sorry. And on the right-hand side, what you see is a single graviton emission process rate, rates for the single graviton emissions. So on the green box, what you see is a massive spin 2 particle decaying into the spin 0 particle that we are looking into by emitting a single graviton. And on the orange box, what you see is the inverse process, or our system decaying into some other state with spin 2 by emitting a single graviton. So to get you an intuition of how this works, it's actually more useful to look into the electromagnetic version of the sum rule. And even better, we can actually use quantum mechanics to understand this. So for electromagnetism, the left-hand side becomes the electric polarizability, which is just a proportionality constant for the induced dipole moment, electric dipole moment, to the external applied electric field. And on the right-hand side, what you see is the single photon emission rates, and the M prime, which was spin 2 for gravitons, are now spin 1 states. And in quantum mechanics, we know a lot of exactly solvable systems, and we'll be actually using the hydrogen atom as a concrete toy model. So let us begin. The Hamiltonian for the hydrogen atom is something that we all know. And we can try adding some small perturbations, which is a constant electric field along the z direction. And this direction electric field induces a shift to the unperturbed orbitals of the hydrogen atom. So here, this N, you can consider it as s orbitals of the hydrogen atom, and m here are just the p orbital states. So when you compute the leading order induced dipole moment, this is the resulting expression. And you can see this proportional, it's proportional to the electric field that has been applied. And you can just take it off and arrive at the polarizability, which looks like this. And when you quantize the photon field, you can actually use this problem to compute the spontaneous emission rate for the s orbitals. And in the end of the day, what you get is this, which you can look up in advanced quantum mechanics textbooks like Dirac's. Now you see what's happening. You see the same matrix elements here and here, and we're just substituting one by the other and arriving at the sum rule. So this is the basics of the sum rule. So we actually derived this using quantum field theory techniques or amplitude techniques. So let's review how we can derive this in quantum electrodynamics. So first of all, what you do is to write the 3-point amplitudes that gives you the process for the decay. And here we're using the on-shell variables introduced by Akanyama, Wang, and Huang, which is also called the massive spinorhality variables. And you can compute the transition rate by absolute squaring this amplitude and summing over the polarizations, which gives you an expression like this. And to compare with the polarizability, you actually need to construct the 4-point amplitude. And here we've used the gluing construction that has been given in Akane, Huang, and Huang in the same paper, where we glue together on the massive M prime line, which is spin 1, which gives you an expression that looks like this. And to proceed, you have to match this amplitude to the polarizability. And to do that, we first write down the effective world line action for the point particle. Here, these E fields and B fields are just the electric and magnetic fields felt by the world line particle. And by expanding in non-relativistic limit, you see why we interpret this AN chi's as electric and magnetic susceptibilities. They are basically the potentials of the world line particle. And because the potential contributes to the free energy, and the derivative on the free energy is what we read out as the induced moments, these alpha and chi's are just the induced, the polarizability and the so-called susceptibilities of the particle. So we now need to convert this into the 4-point amplitudes. And here we'll be using the rule of thumb that we have used to actually show that black holes are minimally coupled to photons and gravitons in a formal work. So the rule of thumb is to take all the photon fields and substitute by the polarization vectors of the photons. And the velocity vector that appears in the world line, you substitute it by the momentum of the massive particle divided by the mass of the particle. And it gives you an expression that looks like this and this with an overall normalization factor n, which you can just fix by comparing it to the scalar QED amplitude, which gives you minus 2m. So now we have two expressions for the 4-point amplitudes. What can we do? Because I mean, they definitely look different. What we can do is to take the non-relativistic and low energy limit so that this propagator itself just pinches into a point interaction. So if you do that, and in the leading order, the expression becomes something like this. And you can compare this expression to this and realize that the alphas and chi's are just something that looks like this. And because we're working to leading order in delta m over m, we'll be dropping this part off, which gives you an expression that looks like this. And we see the same mechanism behind the quantum mechanics happening here as well. So combining these two, you arrive at this sum rule. Now, we have understood how we do in quantum electrodynamics. So going to quantum gravity is pretty straightforward. It's just that everything is different because the photons are spin 1 while gravitons are spin 2. So I think it's nice time to make some side remarks before I move on to part 2. And basically what we derived is a quantum field theory version of the Kramers-Kronig relations. So, and this is a result that is given by Chakrabarty, Delsate, and Steinhoff, where they relate this susceptibility, AC susceptibility, in terms of something similar to energy absorption under external perturbations. And we actually see some missed opportunities. For example, you see a strikingly similar equation in Ira Rothstein's 2014 review. The only difference here is that we need to take omega to be 0 because we're basically looking at static tidal love number. And we have to substitute this matrix element by the decay rates or the transition rates. And because Rothstein only considered the black hole as the ground state, and in our case, we considered black holes to be some state that can decay into a lower mass particle. We add the other side of the sum. That's all you need to do to arrive at the same sum rule. And since final remark before going on is that we use this this propagator when we are doing the gluing construction, but it's more it's more standard to add this decay width to the propagators and when you're doing dealing with unstable particles. So I think it would be interesting to actually look at corrections when we use this propagators instead. So I'll move on to the second part of my talk. And before resuming, I'd like to make an announcement. And this is really a warning, because the rest of my talk is not really going to be based on any concrete computations. So it's really a speculation rather than an argument. But trust me, it's going to be fun. So let's resume and get back into the talk. So let's ask ourselves, what can we do with this? I mean, that's the reason we're getting grants. That's how we get grants. So the first thing that we can think of is to apply this sum rule to black holes, which are kind of the simplest objects that we can think of. And some facts known about black holes is that on the left-hand side, what you see is the tidal love number for black holes, which vanishes classically in general relativity. And on the right-hand side, to best of my knowledge, the only terms that could contribute for black holes are quasi-normal modes and Hawking radiation. And in fact, we know quite a lot of things about quasi-normal modes. So this is the search result for quasi-normal modes on Inspire. And you literally see thousands of papers. So in principle, we can think that the quasi-normal mode contributions to the right-hand side is something that we can compute. So what are we left with? We are left with a quantitative test for the Hawking radiation as single quantum emissions. Now it's a good time to recall how we understand Hawking radiation. So we understand Hawking radiation as a gravitational version of Schrödinger pair production, where one of the pair is emitted out to infinity and we observe as Hawking radiation, while the other falls into the black hole. So this process, we understand it as a single particle emissions. And because the pair, the radiation was created in pairs and one of the pairs fall into the black hole, we believe that Hawking radiation is maximally entangled with the black hole because we have this picture. And it turns out that a lot of black hole information paradox that we see out there in the literature actually takes this as a granted assumption. So in some sense, we have a quantitative test for an assumption that has never really been tested. So I think it's time to wrap things up. Oops, sorry, but I'll just go on. So here I've given you a sum rule for tidal love number, which relates how a body responds to tidal effects, but to the graviton emission rates of that body. And I think we can use this as a quantitative test for Hawking radiation to see if we understand Hawking radiation very well, and which might have implications to the black hole information paradoxes out there. And I think, well, it's pretty straightforward to generalize this to photon emissions because I've already given you a sum rule for the photons. And obviously there are obvious future directions. So we can try to see what happens when we at a nonlinear response to tidal effects or higher multiples. Of course, we know that all black holes are spinning, so we need to consider spinning cases as well. And it would also be interesting to look at higher dimensional or non-flat background cases. It'll also be interesting to look at loop corrections or reciprocated, the decay width corrections. And last but not least, I think we should really run the test. So this is everything that I have prepared for today, and thank you for listening.
Yeah, thanks a lot for a great talk. Let's all thank Jung-Wook.
Okay, so I have a lot of time.
That's fine. We have time for some questions.
Okay, let me just turn on the light again.
Sure. Yeah, so Lance has a question.
Hi, Jung-Wook. Thanks for that talk. I have a question about the connection between Hawking radiation and this sum rule. I thought that the left-hand side of the sum rule was a purely classical quantity in the limit h bar goes to 0. And now you're trying to relate it to Hawking radiation, which I would have thought vanishes in the right h bar goes to 0 limit. So what, I'm missing something.
Well, so I'm not sure if it's known. The left-hand side is computed in fully quantum settings. So I'm kind of regarding.
You want CE to include the quantum corrections.
Yes.
Okay.
Right.
But those will be irrelevant for any astrophysical black holes, correct?
Perhaps, yes. But if you can, well, it's kind of
powers of Planck over m or something like that of the mass of the black hole.
Sorry, I didn't hear your question very well.
The terms that you want that go beyond the classical polarizability,
right?
Will they be suppressed by powers of m Planck divided by the mass of the black hole?
I think that would be, yeah, I think that would be a reasonable assumption.
Okay. Thanks.
Yeah, so I actually have a question. I was wondering, have you looked at, because you were talking about taking the classical limit of QED to get something in ENM. Have you thought about that in the context of coherent states, which are supposed to like mimic the classical electric field?
So which slide I should look at? Let me see. ENM.
Just somewhere in the beginning, yeah.
So you mean this slide?
Yeah, I'm not on any slide specifically. I was just wondering if you had thought about taking the classical limit of QED to like show something about coherent states, I guess, because coherent states are supposed to mimic the classical electromagnetic field, coherent states in QED.
Right. I didn't think about that, but let's see.
Yeah, that's fine. We have a question.
I didn't think about that possibility, so I cannot really answer that now. Yeah.
Yeah, no worries. So we have a question from Alex.
Yeah, thanks. Thanks for the nice talk. In your derivation, you were using 3-point amplitudes, and you were saying something like that you were taking the black hole to have different masses before and after emission. Is that true?
So let's see. So I should probably look at this one, right?
Yes.
Yes. So we are actually considering m prime and n to be different masses.
Where is m prime? Well, you have only one spin of 1 being massive, and
so m prime is massive state with spin 1. So and that's reflected in this expression.
Oh, I see. Yes.
Yeah.
And okay, and the masses are different, and that's why you can use that in real kinematics.
Yes, that's
Yeah.
the reason
Okay.
that we
Thanks.
can use it.
Yeah. Now I understand. Thanks.
Okay, so we have a question from Chia Xian.
Hi, yeah, thanks again for a nice talk. So I just have a basic confusion about your sum rule. So in the case of QED, QED is a UV complete theory. So we can
Right.
compute the entire computing amplitude just from QED or quantum mechanics. But in the case of black hole, the love number is really some UV degrees of freedom. So why is that possible to fix the love number purely from the 3-point, or just purely from the point particle 3-point amplitude?
Let me think. So I guess the sum rule that we derived is actually an effective field theory derivation rather than a UV complete theory. And I don't think it really relies on how we should UV complete quantum gravity, because we are treating the states, the massive states or of the black holes as distinct particle species, which is observable in the IR. So we are basically doing IR effect field theory, and I don't think it really needs UV completion.
But the love number is really a contact information that is not related to the 3-point function. So
It's yes.
still
So basically, what we are doing is the analog of UV completion of the 4 Fermi interaction into the weak interactions, which we see in standard model.
Yes.
It's the analog of that.
So in
And
that, for example, in the 4 Fermi interaction case, it's not like you can use the 4 Fermi interaction. You cannot predict it by just the kinetic term. So it's like the analog here that is really from some independent contribution.
Okay, so I think I've missed your point. So could you explain your point again, please?
Relate the discussion to like selection.
Oh, okay, sure.
Okay, are there any more questions? Yeah, Enrico?
Well, maybe just to follow up on Zhao Shen's comment, like I thought in this derivation here, you're using quasi-normal modes, which are kind of IR degrees of freedom. So I don't know why, Zhao Shen, did you complain about the UV physics being relevant in this derivation?
Yeah, so the 3-point function, if they're just from the point particle action, then I'm not sure where the quasi-normal mode comes in. And the love number is, so imagine if you start with the point particle action, and that gives you the 3-point function. So then the love number is really independent contribution, seems to me.
But isn't what you're thinking about this state, the in-state and the out-state are the same in what you're describing now? He's describing something where the out-state changes, right? Like that's, you have to get a second degree of freedom.
But maybe the question is, what are the outstates that you consider? What are the possible outstates?
You're considering excited black hole, right? Like excited with a quasi-normal mode. That seems to be what you're considering, right?
Are those quasi-normal modes excited too much? I mean, do they have too big a mass gap to let you have a very soft, you want to have a very soft graviton in the transition, right?
Right. So we want the
So are you sure that
quasi-normal
quasi-
modes to be state one excited equation number one.
But isn't there a gap? Oh, I'm not sure, but I thought there was a gap between the black hole and its quasi-normal mode excitation, a finite gap.
I think the gap is like one over the radius scale.
Oh, okay.
Yeah.
Because you could also just rotate the black hole a little bit, and that would give you another state. Is it possible that those are some of the states you're supposed to include in the sum too?
Perhaps, maybe. I'm
They're
not
much
sure.
softer,
I haven't
probably
really
much
thought
softer.
about that. Yeah, possibility. So.
They're like zero modes under a symmetry, so they're softer probably.
Yeah.
Can you get a condensed matter problem where you like think about excitations above the Fermi surface, where you have also low energy modes that you're exciting above some like ground state of a like solid, and you probe that with light? Because that seems to be more analogous to not the hydrogen, but like some solid with a Fermi surface, and then you have small gapped excitation or non-gapped excitations of that Fermi surface.
That's a good point. I think I'll need to look into that problem because I haven't really studied solids that much.